Good morning, functional programmers. Welcome in. All right, welcome to our 10th lecture, Combinators and Staging. Just wanted to give you the state of the house, if you will, or the house is, which is currently blue team is winning. And to be honest, it may not be possible for other houses to win. Depends on if something surprising happens I feel like is worth allotting points for. So maybe there's not hope, but we'll see at the end of this lecture. All right. What? Oh, never mind. But yes, that's the state of the union as it is. All right. Let's go ahead and get started then. Okay. So today we're talking about combinators and staging. To be honest, combinators are a topic I've never really felt super passionately about. And to be honest, I don't think it comes up very often. So this lecture is called Combinators and Staging. It's mostly staging. I'm going to be late on the combinators. Okay. But I didn't change the name of the lecture. All right. But last time, okay, actually, I won't go into last time first. Yes. So here's the Menti code. Copy that down if you so wish. Ask a question, and I will try to remember to go over it at halftime. And if I do not, please remind me, okay? Because I'm supposed to do that. I'll give you a second. It's been going pretty well, I think. Some people have been making use of it, so cool. All right, here's what we got on the docket for today. We're going to be talking about this idea of staging, which is a sort of corollary that comes out of currying, okay? We're going to be talking about how to analyze the cost of a higher order function. We're going to be talking about using HOFs on trees the same way we used on lists in the last lecture, and how we can use HOFs to simplify our programming. This is very much a HOFs part 2 lecture, okay? So, quick temperature check. How do people feel about like the contents of Tuesday's lecture and also Wednesday's lab? Like thumbs down, thumbs middle. Okay, because this will heavily lean on that, right? But this is kind of like a really cumulative idea, okay? Higher order functions are higher order, so we're going to apply them to higher and higher places, okay? And I also have this case study for staging if we have time. But it's no big deal if I don't get to it. Don't feel stressed about it, but it will always be in the notes if you'd like to read it. One thing I wanted to point out again in lecture was if you didn't see my Piazza post about this Hacker News thread I saw over the weekend, or over the past few days. And I just am so unbelievably happy. Like, I cannot really stress to you how importantly I feel that there are literally people out there who do this as their full-time jobs, and they go on Hacker News and they read about their full-time jobs, which are software engineering. And someone said, you know, you should learn this way. You should consult the course material from 15150. Like, I realize you're in this class, right? And it doesn't hit as hard because you're just taking the class. It's just a class. But like, this is that's the coolest thing ever. That there are people in the world you've never met who wish they could be learning what you're learning right here. I just think that's the most amazing thing in the world. Okay, like it's crazy. All right, I cannot get that across to you more vehemently. All right, but diatribe aside, we'll move on. All right. Okay, so last time we introduced this idea of higher order functions, which primarily are functions that take in other functions. And this is a really, really core idea because basically anything you can do, now we can kind of find templates in our code. We can find areas of our code that can be simplified by identifying common patterns and using higher order functions. All right? We learned how we can have curried functions, which take in quotation mark multiple arguments because they take in one argument and they return a function, a lambda, which takes in the rest of the arguments, okay? And then we also talked about the HOFs zoo, the menagerie of map, filter, compose, fold-L, and fold-R, which are our base for higher order functions, but we're going to improve on that as time goes on. Audacity is annoying me. All right. So let's talk about staging, shall we? Okay, and let me set the stage. So why do we do currying? I gave you a little bit of a motivation for why we do currying because I told you about this partial application thing we do. All right, I told you about times where we do stuff like val increment all equals map of fn x goes to x plus 1, right? And I can partially apply this because I don't need to give map the two arguments it's expecting. I can just do this, and now I have a function of type int list to int list. Partial evaluation, partial application is one such motivation. But staging or rather, staging the thing we're going to talk about is kind of a corollary of this. Okay. Another reason why coding is important is we have this idea of a hierarchy of functions. We have map, which sort of captures this idea of let me do something to every element in a list. We have fold, which is this idea of let me summarize all the elements in the list in a prescribed order by applying a particular function. Okay. And so these higher order functions are really just like templates for code. Same way you could write the source anywhere you wanted. I could write increment all recursively if I wanted. That pattern, that template of a function is captured by the map higher order function. So I want to kind of beat this idea into your head that currying is important because it's like specialization. We have foldr, which is a template for accumulating in a list, for summarizing the data. Foldr op plus is a template for summing elements in a list, but you can give it a starting value. And then if I do foldr op plus of 0, that means finding the sum of a list full stop, because I just sum everything and I add it to 0 at the end of the day. So like, if you can imagine in your mind, I didn't actually go ahead and draw one of these, but you can imagine one of them. Like we have this hierarchy, much like the ones we've seen prior in this class, where I have foldr and its descendants of functions that can be defined by it, and the various use cases thereof, right? And this is super, super important because this graph, this tree is extremely wide. Every possible function I can give foldr is a different specialization of this function. For instance, the tlist max function you wrote on your midterm, well, maybe I shouldn't have said that yet, but the tlist max function you wrote on your midterm is just an application of foldr. And you can ruminate on that if that's not clear to you yet, okay? But that's kind of what I had in mind when I wrote that problem. But that's kind of the idea, okay? Specialization, all right? All right, and here's another fun fact for you. And I'll make this claim to you. Syntactically sugared curried functions are trivially total. And yes, that sentence had 3 alliterations in it. Consider the definition of map, like so, written back there. Is Audacity still open? It is. Consider the definition of map as I've written up there, right? I've got this map taking an f, taking a nil, so on and so forth. The question remains, is it total? And I claim to you, it's probably still going to bother me, but that's okay. I claim to you that this function is total. But why should that be? Isn't that a little weird of a claim? Because isn't it true that if I did map fn x goes to x div 0, if I did this on 1, 2, 3, what would you expect the behavior to be? Raise an exception. So why is map total? I just told you map was total, but I just told you it raises an exception. I said map was total. I said nothing about map of this function. Okay, that's the distinction. So before I evaluate this, okay, so let me say, okay, there are 2 different functions I'm talking about, map and map given some f, which in this case is this guy, all right? 2 different functions entirely. So if we unroll the definition of map, remember that like fun map is really syntactic sugar for something that looks a little bit like this, okay? Except not quite, but I'll let you, yeah. So it looks kind of like this, right? I take in the f, and then I return a lambda that's going to do the casing on nil into cons. Does that make sense why that's similar to this, why those are the same thing? I claim to you this is really what map is. So if we look at what map does given any argument, is it true that given any value, I get a value out? Well, if I apply this whole thing to any value, I'm going to always get fn nil goes to da-da-da-da or cons. And isn't fn a lambda expression, which is a value? So for any input I give map, for any v, let's say for all values v of type t1 to t2, for some types t1 and t2, map v evaluates to fn nil goes to da-da-da, or x cons x's goes to da-da-da. Okay? Does that make sense? I always get the same value, well, not the same value, but I always get a value out. But then as soon as I give it the list, it's off to the races, because then what am I going to do? I'm going to go here, and there I might raise an exception. In fact, in this case, I do. Okay? So that's another idea, which is kind of that if I have, fn1, fn, I'm just going to say underscore, okay? I don't care about, I can do this. I just don't care about the argument, okay? fn underscore goes to 1 plus 1. I think I might have asked you some derivative of this in the past, but does this evaluate to anything? Does this reduce? The answer is no, because lambdas always freeze everything inside of them. This is kind of a corollary of that, okay? The exception raising stuff is here. Doesn't matter, or it's here, but it doesn't matter because right here, I return this lambda, and everything in the lambda is frozen in time, okay? Like the plot of Spy Kids 4, all right? So that's the thing that you should realize is that curried functions like map are kind of, quotation marks, trivially total, all right? You can always kind of say that they're total, all right? Cool. But here's another question for you. Is any expression of type T1 to T2 to T3, where it's right associative, so there's parens around this thing, is any such thing total? Is it true that every such thing is total, rather? What do you think? Yeah. Yep, I like that. I get what you're saying. Let's see it. Oops. Yeah, let's see it. So, just because map and friends are is not guaranteed that all of them are. Actually, I'm going to write this out, I guess. Let's do it. So, fun. Actually, let me do it in a val so it's really clear, okay? Val f equals, so fn, let's say, I'm not going to call it T1. I'm going to call it x1, okay? And this thing is of type T1. And it goes to what? I'm going to say a let in end expression. Shoot, I was supposed to define something else before this, but it's fine. Suppose that I defined a function called loop that loops forever on any input, okay? Particularly on a unit input, right? Where I put whatever inside there, okay? Do you believe me that this thing should be of type T1 and T2 to T3, right? Because I take in a T1, and eventually I'm going to return a lambda that takes in T2 and assume that the body here was of type T3, all right? This is actually the example. I just felt like writing it out. And I can define a trivially looping function here called loop that loops, right? Because it gives itself, it always calls itself, right? This is of type T1 to T2 to T3, but it's not total because if I give it any value, what happens? I don't return this. I immediately go and evaluate loop. And what does loop do? Loop loops, right? So we're not going to get anything here. So just having a curried type does not make you total. But if I write something like this, I just kind of screwed myself by using different letters, but x2 equals let's call it E. Let's say there's some expression E that I wanted to return here. All right. I'm not going to define it, but let's say it exists. Do you see the distinction between these two things? Is this one total? This one is going to be total because if I give it any argument, I immediately get back a lambda taking in x2, and then that evaluates to this body. But this loop never happens because it's in a lambda. Because to desugar it, implicitly, what this is it's val f equals fn x1 goes to fn, sorry, I'm running out of space, x2 goes to let ... end. Does that make sense? This is, remember, this is just that, or this is just that, right? So this one is always going to be total because I can't ever evaluate this until I get this. But this one evaluates this let as soon as we give it this argument. All right? Temperature check. How do people feel about that? Right? This is a really important thing to have in your evaluation model of how the language works, okay? You should be able to, like the point of the first 5 weeks of this class is we're building a little mini SML interpreter in your brain, okay? And depending on how good that SML interpreter is, you might get plus or minus points on an exam. But right now is where I'm trying to ascertain or trying to teach you more about what that interpreter should do, okay? So if your interpreter is faithful enough, like this should make sense. And if not, we can work on that, okay? But we're refining that idea, okay? Cool. So here's an example for you. Has anyone built a booth? I'm kind of gonna context switch a little bit here, but it's sort of related. All right. Anyone built a booth? All right. So we build booths, right? We build these big wooden structures. I'm saying this for the benefit of the recording. I know you all know. Suppose you're building a booth, all right, and you've got a bunch of wood, and your friend stays behind at your house or wherever to paint the wood, okay? And then you say to your friend, okay, and you look at like the giant stash of wood that needs to go for the floorboards and stuff, and you say, all right, I'm going to wait for you to finish, and then I'll take that to midway. That's really stupid, because you're wasting time. If I'm waiting for my friend Dave to finish painting the wood, I can still take the giant stack of wood over there to midway, because we need the wood for floorboards, we need it for walls, we need it for God knows what else, things that don't require him to finish painting. What I'm saying is that there's no dependency here. Okay? It's silly for me to refuse to do things just because someone else is doing something, because I can get started without him. I don't need him. All right? This is the idea of staging. All right? You shouldn't have to wait on something unrelated when you can do work right now with what you have. You don't need to wait on other people. All right? This is the idea of staging, which is a term that is describing what happens when you put computations in particular places with respect to curried arguments, okay? And the with respect to curried arguments is kind of the same idea here as what we did, the difference between these two things. I would say that these two functions I've defined up here are differently staged, okay? And that's why they exhibit different behaviors, all right? So let's get into it, shall we? All right. Okay, so the basic idea being that if I want to save all my computations, I can save it until I get all my arguments, but I might not need to, okay? And I'm going to try and recall this example off the top of my head, but I might get some of the names wrong. All right, suppose I'm defining this function, and this is a realistic function for sure. I'm calling a function named horrible computation. All right, and horrible computation, by the way, takes 3 years to run, okay? Sometimes that happens. All right, so this function, horrible computation, I should have put it up there actually, takes 3 years to run, okay? So what this function does is it takes in two curried arguments, it runs horrible computation, and it adds it to y, okay? And suppose I wanted to use this function a couple times. Suppose I wanted to do, it's on the next board, it's fine. Here's the idea also is that I can't stage this because my thing I want to return x and y, x plus y, relies on both x and y. So the idea is I want to move my computations up if I can, if I don't rely on arguments to do them. But I can't do that here, because if I move x plus y in like a let before this lambda, well, how am I going to do that? I haven't bound y yet. If I move it up here, well, I haven't bound x yet. Okay? Let's look at this example, and then it'll make more sense, I think. All right. I don't know why I bothered writing it up. It's up there. Anyways, horrible computation takes 3 years to evaluate. All right. So let's suppose I wanted to do this. Well, what if this is what I want to do? I want to evaluate. It's actually called mystery. I want to evaluate mystery of 2 and 4, mystery of 1 and 2, and mystery of 2 and 5. All right. So how long does my mystery machine take? How long does this take in total? This takes 9 years to run. You could raise a child halfway to adulthood in the amount of time that this takes to run. Okay? So I don't like that very much. But if you notice, what do you notice? What do you notice about this function? What point am I making here? Does this need to take 9 years? Well, it couldn't take 3 years. It could take 6 years, yes. It could, honestly, it could take 18 years. We could run it twice. But yes. So here's the idea. Horrible computation back there doesn't rely on y whatsoever. I don't need to wait to get the argument y before I do the horrible computation, because it's just a function of x. That's all I care about. So I'm gonna give this a switch a little bit. All right, watch this. Boom. I'm gonna erase this. I need to erase this. Put an equals there. F and y goes to z plus y. By equational reasoning, you should be able to reason that this is extensionally equivalent to what I had before. Why? Because z is horrible computation of x, and this is just another lambda, right? So it's equivalent, it's the same type as mystery xy. But all I've done is I've changed the taking of this argument into this let here, after the horrible computation, okay? And then suppose I did something like this. So that was the edit. Suppose I first bound f to mystery 2 of 2. Then I bound g to mystery 2 of 1. Then I used f and g independently after their bindings on 4, 2, and 5, which are the arguments that were before. You probably don't remember. It's fine. How many years does this take to run? 6 years, right? Because I only ever do 2 horrible computations, but now I save a third of the time because I noticed, the thing I noticed here was that there was a common prefix. I was computing mystery of 2 twice. And you should be suspicious when you see something like that, because guess what? Pure computations means you should never have that sub-expression. I mean, you can, like, sometimes it results in clear code, but clear code is not code that runs 3 years after schedule, okay? So noticing this means that we can factor that out, okay? So this is what I call a staged version of mystery, all right? I have staged it such that I have moved this horrible computation with respect to the create argument. I moved the lambda that takes this argument in here after the horrible computation. Does everyone visually like see what I did there, all right? I moved the lambda, right? That is what staging is. We move the work with respect to the arguments because of a lack of a data dependency between them. There's no data dependency between horrible computation and y, so I moved it up. Okay? Temperature check. Up, down, sideways. I'll also take questions. Questions are also an appropriate thing to ask for now. Okay? Yes?
This is kind of a long question.
Okay. We'll see if we have time. This is, I said this last time, this is the bane of my existence, but we supposedly have a lot of time this lecture. All right. Okay, so that is staging, all right? Usually it doesn't matter the order in which we do things. Like I told you, you should be able to equationally reason that this is the same, but sometimes it does matter for performance. Sometimes we do want to care about when things happen. I told you one of the things about functional programming is everything happens, like can happen in parallel. We've seen this with span. It is safe to do stuff independently of each other. In this case, that's still true. I'm just being more deliberate about where I do this. A note I feel like I might want to address is, if you're really on top of the ball, you might say something like, shouldn't, so for the horrible computation we had earlier, you might say something like, oh, shouldn't a compiler notice that this horrible computation doesn't rely on y, and it like hoists it up out of the lambda, okay? Basically meaning that the compiler should be able to optimize that and do what we did manually here. That is true. I claim you don't want that, okay? Not in all cases, all right? Sometimes it's not good if the program does something that you're not expecting. We're being very deliberate here. The cost is here. The cost is here, and you shouldn't expect it here. We're being deliberate also. The source text says the cost is here after you receive 2 create arguments, okay? Good programming is clear programming, all right? I know, like, I have this complaint with like Python where they say, Python, there's one idiomatic way to do things, okay? And then there's also like 20 different syntaxes to do exactly the same thing, okay? Like, there should be one idiomatic way to do things. Yes, I agree, but source text should not have a gotcha. You should never, like, whenever, have you ever come up with something clever? You're like, oh, like, look at this thing I just did. Isn't that clever? Isn't that so cool how it does that? Like, you weren't expecting that. That sucks. Never put that into prod. All right, you never want clever code in prod. You never want clever code. All right, you can keep clever code in notes.txt in ~desktop. Okay, that's fine. But don't share it with people and expect them to write it. Okay, clever code's to look at. Clever code's not to be read. All right. So what I claim to you is like doing that optimization results in clever code, okay, or a clever compiler. The compiler can be clever, just not too clever that it's not what you're expecting. All right. Does that diatribe not make sense to anyone here? Like I don't know. It's near and dear to my heart. I like compilers, but that's just a point I wanted to make. Okay. But yes, no clever code. Cool. All right. Let's move on. This is going to get more important as we talk about things that are not just very extensive operations, because we'll talk about things like side effects, like I/O, like printing, like imperative stuff. Spoiler alert, we're going to get there, okay? And this is going to matter, all right? It's going to matter a lot there. And honestly, also it matters a lot because if I ask you a types question, if I ask you a question on the next midterm saying, is every value of T1 to T2 to T3 total? This is important. Remember your staging, all right? I set the stage. Now you have to walk on. Cool. Okay, now we're going to talk about a little bit of cost analysis of HOFs, okay? Because we have to give that a little bit different of a treatment, okay? If I have a higher order function, this higher order function takes in any arbitrary function. Could be a function that loops forever, could be a function that takes 5 years, okay? But that is something, that is a valid fear. So real fast, I'm going to rewrite map for you, which is our poster child of Hofsville, okay? So if I have x times x's, I'm going to say What do I return here? What's my result? Shout it out. fx cons map fx's. Yes, correct. The question is, how long does map take to run? Okay. So I type annotated there, but let's try to write a recurrence, shall we? So we'll do this in terms of the length of this list. Okay. W sub map. It's actually not exactly correct to say map. Let me say W sub map of f. Okay. For some arbitrary f. If I take in a list of zero length, it's still C naught. We're not getting away from that. And the work of map f given an arbitrary f or a specific f. Well, what do? I do constant work to cons, but I also compute this f here. All right? And the question of the hour is, what does f cost? And I don't know. Okay? I don't know at all. My precondition of map is like, maybe I have a precondition that map f is total at the very least, but I don't know what it costs. So how do I possibly write this recurrence? Well, I'm going to do this, okay? Work of f. Work of f given, let's say this. This might not be exactly good notation, but let's say the work of f on the input x, okay? Plus C1 plus work of map f on n minus 1. Actually, I don't like this. I'm going to say the work of f. Okay? Here's the idea. The work of f is independent of the length of the list, right? Because I just give f x, right? The amount of work done by this has to be independent of the length of the list. So I'm just going to consider it a constant. Okay? We're just going to call it w sub f, right? Because it's not dependent on how this function grows. And if you build this out, eventually you're going to get something like equals da in O of n w sub f. Yes? But as a function of the input size here, that will not change. I'm basically saying, so this is one really weird thing about asymptotic notation, where if something doesn't change based on this, you can literally just say it's constant, even if it really is unintuitive. Even if f is like a function that computes like the n to the nth factorial, and this is 1,000, but it doesn't scale based on n. It doesn't scale based on the number of elements, it scales on what the elements are. But I don't care about what the elements are. My model, by writing this recurrence, I'm saying I only care about the complexity in terms of the length. So it might be bad depending on the elements. And we could actually make it a function of both. If I was really interested in that problem, I might say, oh, map f where the maximum element is k. Then I would have a bound for you in terms of k. In this particular instance, I'm downscoping and saying, my problem I only care about in terms of n. This is not super important. Don't get too caught up on it, okay? I'm just trying to get across to you the idea that there are n calls to f. There are O of n calls to f, okay? And that's all we can say about the cost of this function, okay? We can't do much better than that, all right? Not for a completely general f, not without making more advanced claims about our list or about our function, okay? So it would still not necessarily be wrong to say that mapf is linear work. I just would much prefer that you say something like O of n in terms of the cost of f, okay? O of n calls to f. That's a better story than is linear, and then this w sub f function computes like to the n to the n to the nth factorial. Okay, cool. All right, does that make sense to everyone? Just be more particular about what you say. All right, it is technically correct to say it's O of n. Just don't. All right, w sub f. Okay, cool. All right, we actually have a quiz. I'll address the mentee once you come back. Take your quiz. Sounds like we're all pretty much coming up on done here. All right, how do people feel about that one? Thumbs up, down? Okay, all right. That's enough mediums for me to feel good about it, all right? Cool. Okay, let's get started with the next section, okay? This one may or may not take, well, it will take the rest of the lecture, but it might take a long time. We'll see. All right. We talked about higher order functions on lists. We are going to talk about higher order functions on trees. There's a very tried and true 150 formula where we introduce something to do on lists, and then we do it on trees, all right? And we call that in education. Okay, you ever seen Aladdin? Like infinite cosmic power, itty bitty living space. It's like infinite cosmic power, itty bitty writing chalk. All right, so let's do everything on trees now. We've talked about mapping and folding on lists, but hey, what also stores data and looks like a binary tree? That's right, a binary tree. So what we can do is we can define some functions for us on this same data type. So recall the polymorphic tree data type that we defined some lectures ago. I'm going to claim to you that almost every data type actually that you can define admits a map and fold function. Okay, I say almost every. Unfortunately, there's a very theoretical concern that, or a very realistic theoretical concern that makes that not true. But almost everything can be done. We're going to see how we can do that on trees, though, right? So the idea is like if I have a map on lists, I look at every item in the list and I just change it by applying the f. Same thing with mapping on trees. I take every element in the tree and I apply a function f to it, and I obtain a tree out. Okay, so here's our type signature. It should look very familiar to you because it almost exactly resembles the list definition. It's just that you exchange the tree or the list for tree. Okay, and then we're going to require in this section that f is total. Okay, this is our function. Oh, whoops! I was supposed to write it with you. Let's do it. Let's do it. Don't cheat too much. All right, I'm going to write it in front of you so that I make sure that everyone gets this. Okay, so if I'm going to write it, tree map of f, I'm going to write empty, and then what do I get out from the empty tree? What do you think? Empty. I decided to go and write this while you were answering because I knew it would take a while. All right. F and then node of LXR. Cool. I want to somehow map every element of the tree and apply F to it. Okay. So what's the natural thing I should do here? I got to return. What's the first character I write? Or the first? Yeah. Go for it. Almost. So let's try it. So tree map FL, you're absolutely correct. X, FX, yeah. Yep. We apply F to our root, and then we move on, right? Inductive assumption. If I can map everything else, and then I map my place, I get it, okay? And that's just it. That's just it. It's tree map. It's not, hopefully not the most mind-boggling, okay? Like, again, this sort of thing about recursive functions is like, I don't want you to have to like, try to write this or try to use this on like a big test case to convince yourself of its correctness, okay? I want you to look at it and then in a finite amount of time tell me, oh, this looks right because of the recursive assumption, right? This looks fair. If I map the rest of the list or the tree, I map the rest of the tree, I map where I am here, okay? So it shouldn't take very much brain power for you to think about what this does, because you shouldn't have to think about what it does, really. You think about what it does once, on one step. And if it does it right on the one step, then it's always right, okay? Cool. That's tree map, and I claim to you I can write this on any type ever, almost. All right. Oh, jeez, sorry, typo. Oh, I'm so sorry. So the really funny thing is that last lecture I made a claim to you like, oh, if you write any number of functions too many times, you're going to make a mistake. Okay, I've done this. And I went back and watched the recording. It turns out I had literally written one of the functions on the board wrong that no one pointed out while I was saying that. I did x plus 1 cons increment all, and I didn't write x's. This would have been correct. So no one pointed me out as wrong, but that just goes to show you, all right? Like I've done this stuff for so long. Like I still make some mistakes. So write less code is the idea, all right? We're trying to put ourselves out of business, okay? Faster than ChatGPT can, hopefully. All right. So that's tree map. Let's move on though. I want to do a fold on trees. Ignore what's up there, it's not relevant for this part, okay? I want to do a fold on trees, which means I basically need to go through the tree and apply a function on an accumulator and then kind of update that as I go. But I need to pick an order to do it, and we're going to pick our favorite, which is in-order traversal, okay? This type signature should also look very familiar to you, right? Because it looks like fold. It's just I replaced the list with the tree, okay? This is actually a very deep thing. Like this would be the fact that this type signature looks the same for pretty much everything. Like this is a universal thing. It wouldn't depend on the type, pretty much. But that's how we're going to do our fold function, okay? So let's try to write it out. So, and the neat thing about having these other functions we've defined is now my ensures clause can be just a relationship between code. To ensure that tree fold should be correct, it should be equivalent to getting the in-order traversal and then folding on that, okay? Except we're not going to actually do that. We could implement it that way, but that would be less efficient. It would be space inefficient. It would be I'd have to do it twice, essentially. Better to fold on the tree itself, okay? But this specification becomes very nice and concise, okay? All right, let's define treefold L, all right? Because it's an in-order, well, in-order left-right traversal. Yeah. Yeah, I originally called it treefold, and I was like, but it's not the only treefold. Let me put an L because it's left to right. And then y'all are going to be pedantic on me either way. It's 150 tradition that we should call the accumulator Z. In retrospect, I actually hate that. Like, we've been using ACK all semester. I'm going to do this. Yeah, well, we'll go away after this semester. Okay, if I'm folding on the empty tree, what do I get? ACK, right? Burn that into your brain. Base case, ACK, all right? All right, now if I want to do treefold L on not the empty tree, I'm going to have node of LXR. What's my game plan? Oh, it just occurred to me that you all have my slides. Like, you could totally like just answer everything, every question I ask you by looking ahead. And yet you don't. But yes, don't actually do that. Cool. What do I do? Well, I want to fold in an in-order way. And what is the three words that describe an in-order traversal? LXR, yeah, pretty much. LXR, left, root, right, sure. Yeah, I guess that's an easy way to remember it. LXR, so we want to go left, we want to go to our root, and then we want to go right, if we can, all right? So I'm going to write it in a little bit of a particular way, okay? But here's what I'm going to do. I'm going to say that we're going to let this value, which is I'll call left ACK, equal to treefold L, given my function f, as always, right? And then given my initial accumulator, the accumulator I had entering this function. And I'll do it on the left. I claim to you recursively, this will be the in-order traversal of everything in the left subtree, okay? The result of doing that, okay? Let's assume that treefold L works. If that's true, if that's true, well, what am I going to do? Actually, I'll write out this. I'll make it super explicit, okay? And then I'll get my root ACK, which is what? Which is taking my left ACK and applying it to my root, which is f, given what first? Given the element, because it's of type alpha star beta. So the accumulator comes second. So I'm going to write f of x comma left ACK. And that's how I'm going to get my accumulator from looking at the left and the root. And then what do I finally do? I'm going to get my right ACK, except I'm going to return it. Can anyone guess what I'm going to write? Treefold L what? F, was that root ACK? ACK R. If fold L looked, or fold L R looked scary to you, I actually feel like this looks a lot less scary, right? Because like, what am I doing? I'm just folding the left, my root, and my right. It might not have been clear to you like why I was changing the accumulator in fold L, or why I was doing the F on the outside. But I'm just doing left, root, right? Yes. Well, sure it does. If I say let x1, xn be the in-order traversal of t. Depends on how you phrase it, right? I agree it's kind of harder, right? I wouldn't want to write node of da-da-da. That would be a little difficult, okay? But that's kind of what I'm trying to capture by this specification, actually. It's pretty much the same. But yeah, that's the strength of having these things where we can translate to lists. Yeah. F is not commutative. Well, then you should define your F in a different way. I mean, like, fold L's job is that it only does it, like, well, okay, alpha and beta, first of all, don't even need to be the same type. So if it was commutative, you'd be restricting them to the same type either way, right? So like by nature, we're considering non-commutative functions because alpha and beta might be different types. Yeah. Depends on your operation. If it's commutative, if it's associative, you'll get the same. Actually, we'll see some implications of if that function is associative in a few weeks. But yes. It doesn't matter too much for right now. We're just going to look at it in a particular way. Okay. Are people confused over this implementation? To me, I feel like this actually looks nicer than fold L, but maybe that's just me. Okay. But we just do the thing. All right. And I want to show you how that works, just so that you can see a picture. All right. I've implemented it in a little bit different wording in my little playground. Oops, in my little playground here. Here's what it is. Okay. So in this one, I didn't define root ACK. I just like passed it directly into R. Okay. Does that make sense to everyone? And I also called it left folded. Okay. But this is a tree, right? And the tree just looks like 1, 5, 0, right? That's the test case tree. We're going to try and run folding with the sum function, okay, on this. All right, let's do it. So Mulligan test SML. So if I run treefold on this tree, which is a left subtree of 1 and a right subtree of 0 and a root of 5, what am I going to do? I'm going to enter into the case, and then I'm going to enter the second case. So this is my body of my function, all right? I fold the left with the left subtree, which is just the tree of 1, and I later have to use this result when I fold the list of 0, right? But first, I'm going to fold the left subtree, which is this guy. Then what happens? Well, in place, I'm going to expand this definition of treefold L. This is kind of the picture you should have in your mind for what happens when we evaluate expressions. I leave this here for now, and I go and I evaluate this guy. Okay? We're just expanding expressions. That's all that's happening. So let's do it. And now I'm entering a case. Is my left subtree empty? It's not. It's a single subtree of 1. So I'm going to, oh, wait. Did I lie to you? Is it not 1? It is 1, yes. OK. And now I'm going to do another call to treefold L, where I'm folding the empty subtree, but my accumulator is 0, because I'm now folding the empty that's the left child of this guy. Okay? That's going to return to me my accumulator, which is 0. Okay, and then what am I going to do? I'm going to fold my root of my left subtree, which is the root of this subtree. I take that 0 and I pass it into. Let me not skip over that. Basically, what just happened here is I did the 1 plus 0 for my function. Shoot, sorry, my terminal's acting up. Whatever. Let's move forward. So basically, I applied 1 plus 0. And then I pass that into another call to treefold, except on the right subtree of this, okay, which is empty. So I'm just going to return 1 at the end of the day, right? And now I have my left folded from this subtree. So I take that and I add it to 5. So here we see 5 plus 1, this guy right here. I have the 6. I apply it again. So now I'm into this call to treefold L on the right subtree. But now my accumulator is 6. It's not empty, so I enter into another call. This one is empty, so it's just going to return to a 6. Okay? And then finally, I add 6 to 0, and I get 6. Did that make sense for everyone? Like, I kind of wanted you to just be able to visualize the expressions expanding, particularly for a function on trees. But if you work out the math, like, oh, let me go left here, oh, it's empty, let me go back, oh, it's here, let me go right, oh, it's empty, blah, 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 so on and so forth. But like, you visualize the operations that are left to perform because they're literally still there, right? We're in a let inside of a let, okay? That's kind of the point, right? Any questions on that? Okay. Otherwise, we're going to move on. Yes. OK. All right. Otherwise, if there are no questions about that, I'm going to move on. But we're going to write another function called search. OK? Suppose I want to find something in a binary search tree. I know you must be sick of binary search trees right now. I quite liked them. I had a lot of fun with them. But I want to write a function search that has the following type signature. By the way, y'all are being like super like quiet. Like, are you super confused after the fold L example? I'm just trying to temperature check here. Okay. Like, I'm free to take questions about that, but otherwise I'm just going to move on if you don't have anything in particular to talk about. Okay. We're going to try and do tree search with a predicate function. It takes a predicate function is type alpha to bool. I take in an element and then I return a boolean on whether or not I want to search for it, whether or not it satisfies it. Okay. And I want search to evaluate to the first element that satisfies this predicate in the in-order traversal, okay? So I'm just going to like in-order search until I find something that where P is true, okay? This is a very common pattern, right? We search for things in binary search trees all the time. But this search function will be for an arbitrary predicate. So we will write every single search function right now, okay? Let's do it. And what we're going to do is we're going to return an alpha option. Why? Because it might not be in the tree, okay? All right, search P empty. If I'm searching for something in the empty tree, what do I get? I get none. There's nothing in the tree. What a joy. Okay. Otherwise, I'm going to be in the node case, LXR. What do I do? Well, remember, in order, left, root, right. I'm going to search in the left subtree first. So I'm going to call search PL. Except, I can't use this, because this returns to me an option, right? Because this thing returns an option, right? So remember, if I have a recursive call to a function, you learned this during subless sum. If I have a recursive function to a recursive call to a function that returns an option, I need a case on the recursive call, because I need to decide what to do with it. In most all option functions, okay? So I'm gonna case none. I might run out of space here, but whatever. I didn't really have a choice. Okay. Yes. Sorry, yeah. Not a binary search tree. I'm a binary tree, yeah. Because we'd have to, if we wanted to do this on a BST, we'd have to include a comparison function on this alpha on this alpha type. Yeah. Sorry, slip of the tongue. Thank you. Good point. But yes, we're going to be searching this tree. If I have none, that means I didn't find it in the left, which means what do I need to do? I'm going to do this. If P of X is true, right? If my root is true, then I return sum of X. Else, what am I going to do? If I didn't find, that means it wasn't in my left subtree, and it wasn't my root, so I search the right subtree, right? Search PR. And what is my sum case? What happens if I get sum from my recursive call? I know this is going to be hard to see, but I'll say it out loud. What do I get if I return sum? Just return it. So if I get sum X, I'm going to return sum of X, not X, because that would make it not type check. Well, actually, it might type check. It would just be too constrained of a type. Okay? This is search on an arbitrary binary tree. And it's pretty concise, I think. All right, left, root, right. Like, I don't know. I think these tree functions like pretty much speak for themselves because they claim what they are and nothing more. Okay. Any questions on searching a binary tree? Okay. And we can do this with like anything. We can do it on a predicate that looks for even numbers. We can do it on a predicate that looks for the nth factorial. Okay, so on and so forth. But this can be an arbitrary predicate. Is the cool thing there? All right. And I think that's one, like again, I cannot stress to you how important this idea is. Like these higher order functions, we are writing code that writes code. The code is higher order. The code takes in code. All right. Previously, we had code that was dependent on data. Now we have code that's dependent on code. That is like the most meta and the most impressive thing. Okay. This is such a cool thing. It's so important. I was looking at this over the weekend. It's so important that in Brown's accelerated intro to CS course, they teach it in the second week. They teach higher order functions in the second week, which I thought was crazy. But this is really cool stuff. Okay. Some people believe in a higher power. I believe in higher order functions. All right. Cool. So let's. I would say I have tenure. They can't fire me for that, but that's not true. So don't say anything about that. Cool. All right. Oh yes, I was supposed to look at Menti also, so I'm going to do that real quick. Yeah. All right. Looks like no one had questions. Cool. Okay. There we go. All right. Last subject, and it looks like we're going to be pretty much on time today, which is great. I wanted to talk about how we can use higher order functions to make our lives easier as programmers. Okay, I've already kind of talked about that with respect to these functions like folding on trees and lists and lions and tigers and bears. But the point is that we can use it to make the process of writing code in a really general way, completely independent of what we're doing, easier. Okay, and this is going to be leading into the combinators thing. Although I don't know if combinators is precisely the right term. But let's run with it. Okay? All right. So suppose I have a string of function calls that looks like this, okay? And I'll write it on the board for emphasis, okay? Foo, left paren, bar, left paren, baz, left paren. Well, actually, I don't need to. Quux. Quux always gets me. How dare it? Again, I like predicting myself, but as a next token predictor, it turns out I'm abysmally poor. What was the ChatGPT joke? Anyways. Right paren, right paren, right paren, okay? I already made a mistake writing this. I hated myself every second I was writing this, okay? This was terrible, all right? This is disgusting. Oh, I didn't write it. Okay, yeah, but this is disgusting. Let me try not doing that, okay? If I have to do a bunch of function applications in a row, what do I have to do? If I want to figure out what this code's doing, if I see this code, I say, okay, you're taking x, and you're going to pass it into Baz, and then you're going to pass that into Cooks, and then you're going to pass that into Bar. I'm going right to left, right? But I read left to right, right? I don't read Hebrew, okay? Like I go left to right when I read. So this is not quite what I want to see. I want to see a natural progression. Let me give you an analogy, all right? Oh, well, I'm not going to give you the analogy yet. Okay, here's the thing. I'm going to define this operator. It's going to be called pipe. Okay, and here's the definition. It's just fun. X pipe f is equal to f applied to x. That's all it is. If I have something like, what do I say? 2 pipe int.toString, right? The int.toString library function. This eventually reduces to 2. Does that make sense? So I'm saying the function now comes after the argument. All right? I claim to you this is, first of all, this is an extremely idiomatic functional programming thing. If nothing else you get out of today, like this is the state of the art. Okay, this is what everyone does. All right? And now I can write this. All right, I'm going to write it out on board for emphasis. I can write this. X pipe Baz pipe hooks. I don't know where hooks comes from. Bar pipe foo. And now doesn't that read like English? Why? Because I take X. What do I do to it? I do Baz. Then I do Cooks. Then I do Bar. Then I do foo. It's a list. It's a left to right linear list. Okay? And this is what we get out of this. Because what is this? What is this if not a higher order function? It's a function that takes in a function. So we can do this. But guess what? There's no secrets. There's no gotcha about this, right? Because guess what? This is not hard-coded in. We can just define it ourselves. This is kind of like a diatribe about how SML is nice because there's no gotcha. Like, right? This is just a derivation of what you already know, which is higher order functions. Yes. You could do this though. That would be weird. I have no idea what happens there. X. This is weird. Yeah, I wouldn't want to do that, to be honest. Yeah, essentially this would be like. No, you could do this. It's a tuple of 2 comma int.toString. I claim to you that this is going to be extensionally equivalent to that. Doesn't matter. But I claim to you this is extensionally equivalent to that. Okay? Because you pipe in the pipe operator. Yeah, it's, whatever. Anyways, the point is that nicely, the little curiosities like that aside, this is extremely nice. Okay, this reads a lot better. Okay, whenever anyone does I think that we even have a rule for it. Like if you have, or maybe not, but if you have like 3 or more function calls in a row, you should be using pipe instead. Okay. Let me give you an analogy. All right. I'm making mozzarella sticks. All right. And I want to do this recipe. I heat the oven to 400. I have no idea if 400 is the right temperature for mozzarella sticks. But I heat the oven to 400. I insert the tray of mozzarella sticks, and I wait 2 hours. And then, oh yeah, it's right. It's not because I removed the charred remains. Yeah. And I remove the charred remains of my mozzarella sticks. I love reading my slides and like discovering the jokes I wrote like a month ago live in presentation. Like I wasn't expecting that. But okay, I want to do this recipe, right? Because I'm a responsible adult. But let's see that in SML. All right, suppose I want to make mozzarella sticks in SML. Here's what I'd write instead. I'd say, let me call the function, or actually, let's do it 2 ways. All right, let's do it the first way, and I'm going to conspicuously start all the way over here. Okay, I want to heat the oven to 400. Right? Suppose that heat is like a curried function that takes in this oven value, right? And then what I do is I insert two Z's. Mozzarella sticks. Okay, and this is also a curried function. Okay, and then I put this into wait, and suppose it's like a real, like 2.0 hours. Okay, and then I write remove. Okay, and I'm gonna 1, 2. All right, in SML, this is how I do it, right? But this looks gross, okay? Does this not look gross? I had to like literally go from right to left as I was writing this on this board. Okay, and I don't typically write production code on the board, but that doesn't change the fact that I didn't want to do that. Okay, but I did it anyways. Let's do better. I feel like that's kind of the theme of the past like 2 lectures or so. Like, let's do better. You can do better. All right, you deserve better than them. All right. So let's write it with pipes. So this is going to be separate. Yeah. Let's do heat oven 400. And what do I notice? I notice that it goes as an argument into insert mozzarella sticks. So I do pipe insert mozzarella sticks. And then that itself is an argument to wait 2.0 hours. And that itself is an argument to remove. And doesn't what? Huh? I don't think that would be better. I do not agree. But this is pretty concise, I think. If you look at that and look at this, they look pretty similar, right? Like a recipe sheet has step 1, step 2, step 3, step 4. Here, that's the same thing. I follow my recipe going down 1, 2, 3, 4. This is extremely idiomatic, except for the part where we're writing code about mozzarella sticks. This is idiomatic of the way that we sequence operations, and I think it looks a hell of a lot nicer, okay? So this pipe operator is really useful, and it's just a higher order function. It's just a consequence of being able to write higher order functions, that we can write functions that themselves help us write arbitrary code. This is a higher order function that's completely agnostic to what we're using it for, okay? But it just makes our code nicer. All right, and then it's there in case you can't see the board, okay? But that's how I would write it, okay? Any questions about this, about pipe? 15 minutes, let's go. Okay, all right. I think this is really important, okay? When like my workplace, we use this. When I was employed at Facebook, we use this, right? Like this is the state of the art, all right? I feel like stressing that to you. Cool. Okay, let's move on. So I have some things to say here where like the pipe operator is basically stringing together computations, right? We say do this, then that, but it only works if these operations have compatible ends. And what I mean by that is like this thing better have an input type that's the same as the output type of this, right? And then this thing better have an input type that's the same as the output type of this. It's basically like the same idea as compose, right? If I compose operations, they should have compatible ends. I'm stringing pipes together. I like to visualize it like I'm literally building pipes, and I check the pipes ends and I put them together if they fit. If it doesn't fit, I get a type error, okay? But that's what I'm doing here. So, but suppose I have a example for you here, and this is the example, okay? I'm trying to write a function that will help me find a student's grade. I was in a little bit of an inspired mood when I wrote this, okay? I take in 2 things. I take in a string star string, which is a tuple of the student's name, and the assignment's name. And I take in another string, which is the name of a file on my computer, the path of a file, so like tilde/desktop/150grades.sml or .txt, okay? Or CSV, whatever. And then I want to look up that student's grade on that assignment and return to you an integer, okay? Does everyone like kind of get the problem set up, okay? Like the type signature makes sense? Yeah. I need to find the grades file. This is the path of the grades file.
Oh.
Yeah. Oh, sorry. This is supposed to be find student grade, student assignment, grade file. My bad. Yeah. But like, okay, so like, let me give you an example, which is, I'm gonna write up here actually. Let me do find student's grade, and I'm not gonna pick on anyone in particular, so instead I'm gonna cop out and write Caroline. Hello. Basics, and then string tilde/desktop/grades.csv. I realize you can't see this anymore, but whatever. It's just it doesn't matter. Okay. I claimed you this is what we want to do. Okay. Oh shoot. Okay. All right. This is what we're going to try and do. All right. But let's assume that we have some helper functions to help us out. I've got read file, takes in a file path and returns to me the contents of that file. It's string to string. It's not super clear from the type signature, but it takes in the path, gives me the contents. Okay. It reads the file. I've got parse grades, which basically reads in the data from the file, like the literal plain text. And it, if it's comma separated, maybe it splits out in commas, maybe it looks up things. And there's this type grades here that I don't care to define to you. Okay, it doesn't matter, but I've defined a grades type. I have a grades type that codifies what grades look like. Okay, does that make sense to everyone? I'm just saying that there is a type grades, and that's what this function does. Okay, and then I have a lookup function that takes in this grades value, and it takes in the same tuple, which is Caroline in basics, for instance, and returns me the grade of Caroline on the basics homework. Okay, is everyone clear with this? All right, and these are our helpers. Well, I claim to you that actually I want to do this. Here's what I really want to do more than anything else in the world. I want to write find students. I'm really running out of chalk here. Find fun students grade, student, ASSN, assign, and then file. And what I'd love to do is, hey, what's that little handy little pipe operator I just defined for you? So let's do read file on file, pipe that into parse grades, which takes in, right, because this thing outputs a string. Parse grades takes in a string, so it's type checks. I pass that into lookup, but first I give lookup student, comma, ASSN, and then I'm done, because this return, yes, I'm done, right? Because this whole thing, it's worth noting also that these pipes go last, so this is implicitly this. Okay? Does everyone believe me that this type checks and this does what I purport that it should do? Okay? If you just string together the outputs, this should work. Except this is not realistic enough. Because I said something to you about how this only, so that thing, this only works if the ends are compatible. But these are not the types that they should be. Why? Because I can read a file and it might not exist. So how would I get a string out? I might parse a grade, but it might be complete nonsense. It might be not have commas in it, or it might be written in Cyrillic, okay? It might not be a valid grades file, so this shouldn't always return to me a grades. I can look up a student in an assignment, but wait, last I checked, Caroline is not a student in this class, she's a TA, so this shouldn't succeed at all. So what I'm saying here is that all of these functions, every single one of these functions, should return to us actually this signature. Oops. Should have this signature. Because all of them can fail. Does that make sense? There's a bunch of reasons I just gave you. Each of these operations can fail. And then, does this type check? Because read file of file returns me a string option. I pass that into parse grades. Parse grades takes in a string, not a string option. I can no longer pipe this. Here's what I have to do, all right? So to adjust our definition of this, here's what I need to do. Let me see if I can still do this in place. I hope I can. No, I can't. I have to erase this. Okay, here's what instead I'd have to do. To make this function work, I'm gonna have to rewrite it entirely. If I get none, I give back none, right? If there's no file, I'm gonna return an option finally. If I have sum of S, then I case parse grades of S of, if I get none, I return none. If I get sum of grades, now I have to do case lookup S assign or students grades of, and I should have put it more to the left, but it's fine. None goes to none. Oh my God, okay, we're almost at the end. Some res goes to some res. Did you hate watching me write that? Because I hated writing it. This is disgusting. It's terrible. And worst of all, it's ugly. Okay? You want clean code. You want understandable code. This is understandable, but it makes me want to stop being a software engineer and go be a lumberjack in the woods. Okay? I want to stop writing code entirely looking at this. So let's do better, shall we? Note what I'm doing here. Like, what am I doing here? Every time I return none, I return none. Otherwise, I move forward and I case the next thing, given the previous argument, right? Like, this looks very programmatic. Almost like I could write something that could make my function do this for me. Okay? So here's what we're going to do. I'm going to define to you something else. Has anyone here ever heard of monads? Have you ever heard the term monad? So like a kind of a hypebeast functional programming term. I don't particularly like that. Monads are just monads, all right? What it is it's not important what it is, but it's a tool we can use to help write our code, okay? It turns out that the option type is something called a monad. And the reason why that's important is because we can write this function here. Fun bind, which takes in an alpha option, and it takes in a function of type alpha to beta option. And it returns to us a beta option. All right, this is just the type signature for bind, okay? And what I'm going to do is it's going to do this. I'm given an alpha option, so I'm going to case on it. If it's none, I return none. And if it's sum of x, where this x is of type alpha, right? Because that's how an alpha option works. If I unpack it, I get an alpha. I can now have a function f, which I can call on the alpha, and I will get out a beta option, which is what I purported to return. Is everyone clear on that this type checks? Like, this makes sense that this type checks? We're going to see how we can use it, okay? And this actually kind of looks like what we were doing here, right? Like, it resembles this, like, looks like that logic. Now we're going to rewrite it entirely, okay? So here's my claim to you. Here's my claim to you. Be gone is my claim to you. Be gone with ugliness. Be gone with inefficiency. We're going to do things better. I'm going to use this bind function. I need an alpha option. So what am I going to take in? I'm actually going to take in, I believe, some. Actually, no, sorry. Let me start off without bind. No, I need to start off with bind. I'm going to take in sum of file, and I'm going to take in another function which is read file. Oh, sorry. Actually, sorry. I'm going to show you because I don't have a whole lot of time. Okay. Blah 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 blah. Here we go. Yeah. This is way better than me writing it out. Okay. I claim to you this is what we're going to write instead. Okay. Oh, that was it. Except I did it differently. I defined bind for you just now as a tupled function, but actually strike that. We're going to define it as curried. Okay. Cool. This is what we're going to do. I say, let me do read file on the grades file, which will return to me an option. Then I give it a lambda, which takes in contents, which are the contents of the grades file, and it gives it to, what do? I do bind of parse grade. I parse the grades with the contents. Then I give a lambda that then takes the grades and looks up the student assignment. There should be a grades there, sorry. This might look like incomprehensible nonsense to you, and in some sense it kind of is. But the point is, when you see this, you should see something like sequencing. It's sequencing. It's like pipe. I'm saying do read file, and then do parse grades on what you returned, and then look up the student assignment, and then the missing grades. Okay? And I understand this is a lot, so like you might not see exactly why it does what we want, but I claim to you that the thing I just erased, it is extensionally equivalent to that. It is short-circuiting. The bind operator takes care of that for us. Okay? Another thing I'm going to tell you, first of all, I'm going to claim to you this is much more readable, but not quite enough. I had to write bind everywhere. Okay? Some enthusiasts like defining this guy. They say infix. I don't really have space, but
Could you try again?
No, I can't. How did on earth? Okay, interesting. In the middle of my lecture? Come on. Some people like defining this greater equals operator in Haskell. They really like this. This is like the symbol of the language. They get really nuts about it. Okay, it's just a monad. It's just a pipe. But the point is that now instead of that, we can actually write this. And doesn't this look nice? Here's what it's doing. Okay, greater equal is just an infix operator that is equivalent to bind. So this is the thing I'm binding. This is the thing I do next. The way you should think about this is that this is an operator. Bind is an operator that takes in a function f. The function f is what I do next. It's like the pipe. When I pipe, the right-hand side is what I do next. But now this thing I do next is only invoked if the left-hand side thing didn't go to none. Otherwise, the whole thing goes to none. And you should see this in the type signature, right? We're building pipes. Why? Because I take in an option. I can optionally unpack the option and then produce a new option, or I produce nothing. We're stringing together operations that potentially have fallible output types. That's all it is. So I can rewrite my function as this, and I think this looks so much nicer than blah, 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 blah. This eldritch nonsense, okay? What on earth is this? This is a -10 as style points, okay? Tell you what it is. So let's do better. We did better. This is better, all right? Blah, 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 okay? Any questions on bind? This is not like strictly course content, but this is a really important application of higher order functions, okay? Like this is a general pattern that makes programming, period, full stop, with pipes or with anything better, okay? With optionals, when we have things that might fail, which means that it automates error recovery for us, essentially, okay? I can't necessarily motivate this super well, in a sense, without giving you like a whole software engineering like a whole software engineering year into your brains. But if you ever get the chance to use this, you will. This is really important, okay? And you can use this in like pretty much any language. Okay, but this is bind, monadic bind, all right? And the idea is just at the end of the day, readability. I want readable code, okay? Blah, 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 blah. This was a bonus. You can look over it if you want. I put it there as a bonus specifically because if you look at it, if you don't get it, like I think you'll be fine. Okay, it was just more examples of staging. We're right on time. Please fill this out if you care to. I really appreciate the people who've been filling out every week.